I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University.
And I'm Vladimiro Mujica. I'm a professor of chemistry at Arizona State University.
So today we're making a video to introduce the first part of fundamentals or background from Atkins' book in Physical Chemistry for the Life Sciences. And you can find more information at a website we have, biopchem.education, where we'll also upload the videos and any ancillary material that we talk about. So Atkins' book, Physical Chemistry for the Life Sciences, we're going to be looking specifically at the fundamentals component. But what we're going to be going through in future lectures is kind of through part one of this book, Biochemical Thermodynamics, and really making a video on each one of the chapters of this. So each kind of separate chapter in thermodynamics. So this fundamentals starts, and it has three main components. It talks about, it's all background material you've seen in introductory chemistry and mainly chemistry classes, and it goes through atoms, ions, and molecules as a reminder, kind of bulk matter, and then the concept of energy. And so it starts, fairly crudely with chemistry, with where we always start, which is introducing atoms, how they bond into molecules, reminding us of how we would kind of conceptually draw or schematically draw bonds versus lone pairs versus organic molecules, etc. So, and then we kind of move from this level to when we get a little bigger, right? We often go to kind of ball stick models where the colors represent the type of atom, the size is often tried to be indicated as well, etc. So oftentimes we move up to kind of this stage when we move to kind of biological molecules, but where we're still looking at molecular level detail. From there, from this kind of molecular level detail, when it gets to too many atoms, we often move away from showing individual atoms and bonds or explicit kind of electronic structure to looking at things where it's following, for example, here in what's commonly used in peptides and proteins, where it's showing kind of, walking a backbone of something. And there we move from kind of molecular structure, or called primary structure, where they kind of use dots for each of the amino acids, to ones where it follows the backbone, or through this type of molecular peptide interaction, it just follows that backbone, and this is showing, for example, a secondary structure of an alpha helix. So, just basically how it's templating three-dimensional space, how the entire thing looks like in three-dimensional space. And this is important because oftentimes it's not a single peptide or protein subunit, but they're often multiple subunits, or they're often dimerized, or in this case, as the book shows, a tetramer as being its overall quaternary structure in a system. And it does the same thing for other common systems like nucleic acid systems, how you move from the molecular level up to more diagram-based schematics, and things like lipids in showing a bilayer or micelles, etc. And so I think of that as all kind of rudimentary background of reminding us of some basic chemistry. Any?
Well, the only thing I would like to say at this point is that when we look at we see this type of representations here. Look at
the other side. Yeah.
The other side. So we see here this ball here is supposed to represent one atom, and this another atom. So there is a color code and there is a size code to indicate which type of atoms it will correspond out of this list. Now when we think about molecules that way, we are overly simplifying the description of a molecule. Actually, without a branch of physical chemistry that is called quantum mechanics, or a branch of physics, we have no understanding whatsoever of any of this. I mean, each time we represent this is the end result, where we are trying to summarize that molecules, they have a structure, they have a geometry, they have bonds, and if we want to look in detail about these bonds, it would be electrons, and if we want to look in more detail, there would be electrons closer to the nucleus and electrons closer to the bonds. So it's just that don't lose sight that molecules are extremely complex objects. But when we go into biological description of molecules in biology, we try to simplify things and try this type of representation of molecules.
Yes, exactly. But we often need these kind of representations. But you're right. Oftentimes we oversimplify what's going on, through some of our schematics that we use. So part two, kind of, I've done this in a very boring way, which is in a sense showing a bunch of tables, which I think is horrible. But it basically, just reminds us of bulk matter. It reminds us solid, liquid, gas, and it spends a lot of time, like a lot of books do in introductory chemistry and even in physical chemistry, where because gases are one of the easier things to initially explain, it spends a lot of time just kind of reminding us of equations of state, but it stays very simple, like ideal gas law or stuff like that. And the thing I do like to point out here, though, is, and I do like that the book does, is it spends times really, this one was meant to represent mechanical equilibrium, and it has another diagram for thermal equilibrium. And I really like that because really at the heart of thermodynamics, one of the first concepts that really needs to be understood by students is this concept of what equilibrium is, and how that relates to, entropy maximums, energy minimums, etc., and how you find what equilibrium is in certain systems. And also what I would call the really practical. Statistically, the number one thing students miss on exams or any type of evaluation in physical chemistry, converting units. Just the basic algebra and converting units and using the wrong constant, not understanding, a Boltzmann constant versus a gas constant, or converting calories, joules, different ways to express, units. And it is, while it's very simple, it's also something that, the devil's in the details oftentimes.
Yeah, and very much so. I just wanted to, again, how concepts are complex, and even though they look very simple. You said that this represents a mechanical equilibrium, and it is true. This is a wall, and these are supposed to be molecules colliding with the walls. But the moment we take into account the possibility that this molecule collides with that one and they collide among themselves, then we are led to another aspect of equilibrium, which is thermal equilibrium. That is a combination. So now we have thermodynamic equilibrium. So thermodynamics somehow brings together mechanical concepts plus temperature-dependent concepts, thermal. And the fact that we can put these two things together makes a huge difference, because in biology we need both of them.
Yeah. And then finally, over half of it is dedicated to just reminding us of energy. And I think that's wise. When you really think at what you're doing in thermodynamics, 9 times out of 10 what you're looking for is energy related in some way. Half of the confusion of thermodynamics is just that we constantly change what type of energy we're looking at. Instead of looking at the internal energy, it's often more useful to look at the enthalpy or the Gibbs free energy, depending on what mechanical or thermal variables are being held constant in a problem. But it all, and then in quantum mechanics, the same thing. When we're writing down Schrodinger equations, etc., it's usually back to looking at energy. And oftentimes students, it's important that they realize why we move to some, why do we do, like you said, work and heat in thermodynamics, but we do more traditionally kinetic and potential energies in quantum mechanics, etc. It all gets back to what's convenient, frames of reference for looking at energy. And again, just as an additional thing, it took about 200 years, probably more, to understand that heat is a form of energy. Yeah.
It sounds like crazy. Come on, this is supposed to be okay. No, it's not. When we look at a thermodynamic process, we have to separate work and heat And the fact that we could add together work and heat took about 200 years to understand. And the effort of extremely clever people. And this is one of the essential differences between pure mechanical systems and thermodynamic systems. That we can do this. And then the other key concept that we are not going to exploring now is entropy.
Yeah.
So thermodynamics is about the interplay between these
Well,
two
and
guys.
this is really, this, connection, like you said, took, a long time, but and specifically getting to the molecular level, right? Like, this is really the gateway, into, molecular level details of thermodynamics and statistical mechanics, statistics of large numbers that gets us there. So the book starts with what I would say is, often students' first introduction into energy, which is electromagnetic radiation, and just reminding us of some very basic concepts, but putting it in the context of what they're going to see later on, of spectroscopies that you normally see in biochemistry or chemistry, et cetera. And then it moves on to the stuff that they've seen in introductory chemistry, but they definitely haven't explored in near as much detail as we're going to get to this semester, which is, breaking it down into more and more fundamental types of energy and getting a molecular picture for what some of those are.
Yeah, and this is extremely important, even if we want to understand at the cellular level how energy is exchanged. Because this decomposition, energy decomposed in translational energy, rotation, vibration, and electronic, is essential to understand how an extremely basic cellular process or a DNA process, a mutation. What does it imply, a mutation, in terms of energy exchange? Do mutations happen at random? Do mutations happen because of a certain rule? This is one of the most fascinating problems in modern biology, how to understand how a mutation is preserved or dies through evolution. And this is a question, we don't have an exact, there is an answer for that in evolutionary theory, but we are not going to go that far, but we want to understand how energy is really used at the molecular level and what type of
Well,
processes.
if you don't, having an intuitive feel and getting some real fundamentals for these different molecular level degrees of freedom, I think is one of the key things they get out of physical chemistry, and that really translates to, as you've said, to the real biological world, to real life processes, to things at the macroscopic level. The intuition we can get from some of this is critical.
Right, and just another simple example. You're lying on the beach, and then there is energy coming from the sun. Where does it go? Where does it go to translation of a molecule, to a rotation, to a vibration, to an electronic transition? And once you have absorbed this energy, what are the processes that are triggered by this absorption of energy? These are the type of things that we really want to discuss here.
Yeah, in detail. So, and then it ends with kind of giving a very, what I would say, often almost everyone's seen from introductory chemistry, example of kind of how it goes from, looking at things at a chemical or molecular standpoint from just kind of kinetic theory of gases. And so it just briefly reminds us of something we've seen in the past, that the temperature can affect not only the average speed, but the distribution in speeds, and that there are these large distributions and stuff, and that you could also do that with, different variables. You could change that and look at how the mass, changes those, et cetera. So it only does it in a few pages, but it tries to remind us that we've seen a lot of these concepts in the past, and we're going to use them as the building point for real complex biological systems. So, and then finally, in each chapter, and I'm glad they did this in the fundamentals as well, they really try to take interludes to build mathematical toolkits. And I know you and I both strongly believe in, math is the language that we need to use to describe any science. So, honing that language so that you have as big a vocabulary and can express yourself as good as possible is to me critical in science. And so I was glad that they even started with something that oftentimes students forget, exponentials, and how those exponentials, often people just think about some type of decay, but how those also define one of the more important symmetric functions they'll ever run across,
Right.
Gaussian distributions.
Yeah, and this is so important. I mean, it's impossible to exaggerate the importance of this. And the other thing is how to translate the mathematical language to biological processes, or how to make connections. For instance, if I tell you that an earthquake was, I don't know, 5 in Richter scale,
Right.
how does that compare to the pH scale?
Yeah, and
Is
they
it the same or is it different?
Right. Well, and there's only a few concepts that you see so often, these scales of logarithms, these scales of powers, but like you said, and we're not talking even just science, exponentials often get most introduced in economics, it gets,
or bacteria.
yeah, I mean, so it's so critical. And I would go one step further on the practical side of this. Students, when you see this, not only should you be able to kind of, go back and look at your, in this case, just basic algebra or logarithms and stuff, you should be able to plot these. You should be able to, do things where you can graphically look at the mathematics. I think whether it's using symbolic codes like Mathematico or just spreadsheets to plug in some numbers and see what these look like. I think oftentimes interacting with the mathematics, not just with the science, but just fundamentally really helps, students to concrete their, understanding of just basic mathematical concepts.
Yeah, and finally come to the realization that there is no learning thermodynamics or kinetics or any physical chemistry without math.
Yeah, I'd go further. I would say name a scientific field where you can, learn anything without, if you keep asking why long enough, you're gonna need to, hit mathematics to really give you a concrete way to explain any type of science. Yeah. So anyway, that's kind of an interlude into what you can tell we consider important, which is making sure we build some of the fundamentals as we go through this as well. So with that kind of gives you an overview of what was covered in the fundamentals. We'll continue on with videos on each individual chapter within this. Thank you.
Thank you.